Good afternoon. We're going to continue on today with our stuff on utility theory and risk aversion. Let's see, this looks good. Oh no, this is a small one. How was that? Good. Let's see where we are. We were working that example that showed about risk aversion. So let's get at that. And before that, let me talk about the midterm. It's really not a midterm, it's a little later than a midterm. But let me schedule that for Wednesday, July 9th. That'll be after the break. Wednesday, July 9. And I think we're going to make the exam a little longer than 50 minutes because we have everybody is online. So I may make it about an hour and a half to give you a little more time. 15 minutes is not really a whole lot of time here. Okay, this will give you some idea. You'll be able to study over the break if you want, but also before we go on break this week, I will make up the exam and talk about it before we go on break, so you could know what to study over break. Typically what I do is I tell everybody what the topic of each question is and how much each question is worth. So we'll try to do that here too. Now, let's see where we are. Let's see if this other pen is a little better. Maybe. Let's see if our example satisfies maximizing expected utility. We saw it didn't maximize expected gain. So remember, we had these two lotteries. Lottery 1 was like the following. Lottery 1, you have a 50-50 chance of either getting $10,000 or losing minus $5,000. In Lottery 2, we have a chance of 50-50 chance again. But now, on the positive part, we can gain $4,000, or we could gain nothing, $0. Okay, now, we said most people pick Lottery 2. Decision makers select Lottery 2 to play over Lottery 1. Lottery 1. Even though, let's let's write this out on the next page. Even though the expected value of lottery 1 the expected value of lottery 1 equals 2,500 equals 1/2 times the 10,000 minus 1/2 times the 5,000, which is strictly greater than the expected $2,000, which is equal to the expected value of lottery 2. Okay. So now let's look at the utilities. Let's calculate the expected utility for these lotteries. Okay. So in lottery 1, we have the following. Lottery 1, I think the data will like this. If they're not, we'll just pretend they are. We had $10,000, and we had minus $5,000. Okay, and so this was equal to 1. We set $10,000 equal to 1, and we set the minus $5,000 equal to let's do this, the utility of 10K. And the minus $5,000 was equal to minus 9 equals the utility of minus 5K. Remember, we calculated that second. Okay, now versus lottery. So the expected value of lottery 1, the expected utility of lottery 1 is what? Utility of lottery 1. Now we take those utilities equals, and we also have 1/2 and 1/2 here, equals 1/2 1 plus 1/2 of minus 9. So what does this equal? This equals minus 4, right? Because it's 1/2 of minus 8 here. Okay, now what about the expected utility of lottery 2? So expected utility of lottery 1 is negative. What about utility of lottery 2? Let's look at lottery 2. Let's draw these out a little more. Lottery 2. Here we have 1/2, 1/2 again. And here, what did we have? We had 4,000 on the upper side. And we said the utility of 4,000 of 4K was equal to 0.9. I hope that's what I gave the last time. That's what I think. That's what I have written down on here. And the utility of $0 is just equal to 0. Okay. So the expected utility of lottery 2 is simply 1/2 times 0.9, 0.9, plus 1/2 times 0 equals 0.45, which is clearly greater than -4, which equals the expected value of utility of lottery 1. Okay, so our choice of lottery 2 is consistent with maximizing the expected utility. So the choice of lottery 2 over lottery 1 is consistent with maximizing expected utility. Remember, we said that if you satisfy our 3 axioms of utility theory, then maximizing expected utility is always optimal. Now, remember we said that, recall that a decision maker is risk averse if and only if the decision maker's utility function is, and we want this strictly concave. Remember that concave functions are cave-like. Is the easiest way to remember them here. Okay, now let's look at some concave utility functions, because sometimes we would like to fit a utility function to some data. It would be a good idea to fit ones that we thought are risk averse, because risk aversion is very common. Okay, now there are people who are risk seeking, like the people who go to Las Vegas and gamble. But they may be maximizing some entertainment value here. Okay, let's look at some concave increasing. We want utility to be increasing, because increasing satisfies our economic criteria of more is better. This is like they have the little girl on the AT&T ad, always wants more. In economics, we always assume more is better. In fact, you might say, well, suppose I go out for pizza, and instead of getting 2 slices, I get 2 whole pizzas. And I can't eat 2 whole pizzas or I'll get sick. The economist would say, well, you can give the extra pizza away, or you could even sell it. So more of a good thing is always better. Okay. So let's look at common increasing utility functions. And we have a whole host of them. Let's do one, the exponential and we'll call it negative exponential. Okay, good. Here we say that u of x, utility of x, equals b minus e to the minus alpha x. Typically, here we have alpha must be greater than 0, and typically b equals plus 1. So you start off at 0, and then you try to end at 1. So you are concave here. 2 is logarithmic. Which of course is related to exponential here. And here we have u of x equals, let's just let it equal to the natural log of x. It could be the log of some other, the log to some other base, but let's just take a natural log here, okay? Where x is greater or equal to 0, okay. Well, let's let x be strictly greater than 0, okay. Then we have the power utility function. Okay, and that is u of x equals x raised to the power b, where b is less than or equal to 1 and not equal to 0. Okay, otherwise, if it's equal to 0, it would be the same for any value of x. Okay, now finally, we're going to have the so-called quadratic utility function. The quadratic looks like the following. U of x equals x minus bx squared and I think in the text we see 1 minus 1/2 bx squared just to make the math easier. And here we have that b is greater than 0 and also that x is greater than or equal to 0 and less than 1 over 2b. The reason that we want this here, this less than 1 over 2b, is that so u of x is increasing. When it equals 1/2 b, then we get 0, of course, here. Okay, now, so these things have some nice properties. They're increasing. 1, 2, 4 are increasing. these four utility functions are all increasing. They're all continuous. They're increasing. They're not only continuous, but they're differentiable. Remember that a differentiable function must be continuous, but being continuous is not enough for differentiable functions. We'll call this smooth. Because a function like this x, if we plot f of x versus x and take a function that looks like this, this is continuous. And let's call this point A, B, C, but not differentiable. It's not differentiable at A, B, and C. And why is it not differentiable? Because the left-hand derivative you could consider that the slope of the tangent there is not equal to the right-hand derivative. So these kind of functions like this piecewise linear function here, or you could even have a piecewise a polynomial function, is not differentiable at a finite number of points. Now we can even, there are special functions that are not differentiable everywhere, but let's not worry about that. Okay. Now, one other thing we want to look at is another property, desirable property, of a utility function is that it be decreasingly risk averse. Okay. Now here we're going to have to worry about the second derivative of the utility function. Okay. Decreasingly risk averse, what does this mean? That is, the more money we have, let's call this X, the less risk averse we are for a fixed number of dollars. Okay. This is like, take Bill Gates. If Bill Gates is flipping a coin and he says, well, if you get heads, I'll give you, I'll take $10,000, and tails, I'll give you $10,000. Now, Bill Gates has an enormous amount of money, so this $10,000 to Bill Gates would just be like pennies for us. So it would be the same as us betting 10 cents on a flip of a coin. So the more you have, the less risk averse you are for a constant amount of money here. And how do we measure this? Quantify how should we quantify this? Here we get to something called we use the Arrow-Pratt absolute risk aversion coefficient. Now let's call this A of X. Okay, where we have that A of X equals what? Equals minus the second derivative of our utility function over the first derivative of the utility function. Now, we have the minus here because concave u of x has negative u prime prime of x. So we want this thing to be positive, this Arrow-Pratt absolute risk aversion coefficient. And why do we have this divided by the first derivative? This is to normalize A of x. So let's put minus, gives us A of x is always greater than or equal to 0. Okay, now let's calculate this Arrow-Pratt absolute risk aversion coefficient here. Before that, let's say something. Therefore, we would like a desirable property utility functions to be concave, reflecting risk aversion, because almost everybody or every company is risk averse. And we want, and A of X be decreasing with X. Okay. So we want their absolute, their coefficient of absolute risk aversion to be decreasing. So we would like them to be risk averse, but decreasingly risk averse. So the DM is decreasingly risk averse. Obviously, we don't like increasing risk aversion, because that says that you get more and more risk averse the more wealth you have, which is silly, I think, here. Also, obviously we would like the utility functions to be continuous, differentiable, and increasing. Continuous, differentiable, and increasing. This increasing is more is better. Which is one of the fundamental axioms of economics, that more is better. Okay. Let's calculate A of X for some of these utility functions. Compute A of X, this Arrow-Pratt coefficient of absolute risk aversion here, and we should have pointed out here. Let me point it out now that Arrow is a Nobel laureate. In economics. We may go into what his main contribution would be for group decision making, something called social welfare. It has nothing to do with welfare, but has to do with optimal societies and distribution of goods. Okay, let's compute A of X for, let's do it for, do it for the following. Oh, here, must be here. Oh, yeah. Let's do it for utility functions, U of X, in number 1 and number 2. Okay. So what I mean in number 1, what do we have? Number 1 is the exponential. And number 2 is the logarithmic utility function. So let's do those two. Plus for extra credit, and you can have that due this coming Friday if you like. And in fact, you can even turn it in during the vacation or a little after the vacation. It matters not. For extra credit, calculate A of x for the utility functions (3 and 4), and tell whether they are decreasingly increasingly or constantly risk averse. Why don't we say, instead of they are, why don't we say they represent, is a better way to say it, utility functions. We'll do it right now for number 1 and number 2. Okay. Okay, so let's do it for oh boy, we're out of paper here. Let's see what we have here, the gang. Seems to me that we're running out. Yeah, we got enough to finish up, I think. Excuse me. Okay, so let's look at the first one. Let's look at exponential. And this exponential is the following. And this is really negative exponential, of course. And we'll say that these have the general form of, let's set b equal to 1. Let's set u of x equals 1 minus e to the minus alpha x here. And here's where we have alpha is greater than 0, strictly greater than 0. Okay, so what is this guy? This guy starts off at 0 and goes up to 1 here. Okay? So let's take the first and second derivative. So u prime of x, the first derivative, equals what? Equals alpha e to the minus alpha x, right? Here. The 1 is the derivative as is 0 with respect to x. And the second derivative of that is what? Equals minus alpha squared e to the minus alpha x, okay? Okay, so then, therefore, what do we have? Therefore, say hence, we have that A of x, the coefficient of absolute risk aversion, equals the second derivative minus u prime prime of x over u of x equals what? Equals minus, and u prime prime of x is minus alpha squared e to the minus alpha x over alpha e to the minus alpha x. Okay, so now clearly the e to the minus alpha x it cancels out, and what do we get? This equals this just equals, and the minuses cancel out, so this just equals alpha. So what does this mean? So u of x is constantly risk averse. Again, we should say represents, it's a better way to say it, represents constantly risk averse u of x. Okay. So it just equals alpha at all times. So no matter what x is, the coefficient of absolute risk aversion is always the same. Now, this is not as desirable, but it's not as bad as being increasingly risk averse. Now, let's look at some other guys. Let's look at number 2. Two was the logarithmic utility functions. So let's look at the general form of logarithmic utility functions. And here we say that u of x equals the natural log of x. Now we could also have the log to some base, to the base 2, the base 10, whatever you would like. But let's just take the natural log, that, and let x be greater than 0. Okay. So what happens here? Now, the first derivative of the log is simply 1 over x equals x to the minus 1, right? And the second derivative of the utility function, it's easier to think of this as x to the minus 1 equals minus x to the minus 2 equals minus 1 over x squared. Okay. So a of x equals minus, we always have that minus, then we put the second derivative on the top, minus 1 over x squared, all over 1 over x. Okay. So now, simply multiply the top and the bottom by x. So we multiply the numerator and the denominator by x here. We obtain that a of x equals 1 over x. Okay. So what is this? So this is decreasingly this represents a decreasingly risk-averse decision maker. Okay. This is decreasingly risk-averse. Okay, good. Okay. Now, okay. Oh, here, let's do a couple of paradoxes of utility theory. These are cute. Okay, and the first one we'll talk about is this could really be a paradox of expected value. It's called the St. Petersburg paradox. Okay, and this was developed by Bernoulli in the 1700s. Well, this is an old paradox. And this is one of the famous Bernoullis here, famous in math and physics. Okay, suppose we have the following game. You are presented with a chance to play the following game. Okay. The game is very simple. It says that you flip or toss a fair coin a number of times and stop when you get the first head. Okay. Now, if you get the first head, on the first toss, let's do this. On first toss, you get the first head on the first toss, you receive $1. If you get the first head on the second toss, then you receive $2. If you get the first head on the third toss, let's make that third toss, you get $4. So it keeps doubling. If it's a fourth toss, you get $8. Fourth, you get $8. Okay. Now, how much would you pay to play this game? Some of you have probably seen this, but this is a good thing when you go out drinking with your buddies. You can test them on this and see how much they would pay to play this game. Okay. Now, most people would say, well, I don't know, I could play $5 or $10 to play this game. Would pay, I would say, less than $10 to play this game. Okay. Now, what is the expected value? A fair price for this game, let's call it a fair price for this game, would be the expected value of the game. Okay, so we'll say that a fair price for the game should be, what do we say, should be related to the expected value of the game. Now let's calculate the expected value of the game. So the expected value of the game is what? Equals 1/2 times $1. So this is the probability of heads on the first toss. The game would stop right there. You would get your $1. And suppose you get a tail on the first toss, and then you get a head on the second toss, plus 1/2 times 1/2 times $2. So this is the probability of a tail, and we get the head on the second toss here, and 2 is our payoff. Plus what? Suppose we get the first head on the third toss, so we have plus 1/2 times 1/2 times 1/2 times $4 here, okay? So here is the probability of tail, probability of tail, probability of head. Okay, and this goes on forever. Okay, so what do we have here? This equals what? Equals 1/2 times what? Times 1. Now, one of these guys cancel, plus 1. Now, two of these guys cancel, plus 1, plus 1 on forever, equals 1/2 times what? Times infinity. Equals an infinite amount of dollars here. Okay, so we have an infinite amount of dollars here. So you people that were only paying up to $10 for this, the expected value of this is an infinite amount of dollars. So how did Bernoulli change this? Here, the expected value of the game, we don't have a utility function. We say the utility function is, this is a utility function. U of dollars is linear. But Bernoulli said, well, suppose U of dollars is logarithmic. Okay. Equals the natural log of dollars. Then you'll see that you'll get a finite, this yields a finite what we have here, yields a finite expected value. I'll give another extra credit on this next time. I'll look at the log of the base 2 and see if we can calculate that. That's a good extra credit, actually. Okay, good. Thank you very much. We'll see you tomorrow. We have a little bit more to do on utility theory, and then we're going to move on. Thank you.